Hello everyone. So today we're going to continue on 14.6. So our last video talked about Taylor series as well as some very common power series of e to the x, sine x, cosine x, tangent inverse x, and natural log of 1 plus x. So after reviewing those power series, now we're ready to actually use it to solve differential equation. So what happened is when we run into differential equation, if the differential equation is written in the following way. Maybe I'll write it this way. Solving differential equation using power series. So the general idea here is that when we run into differential equation that might not be solvable by other method, we might be able to generate the solution using some kind of Taylor series or power series. And by doing so, even though it didn't give us the exact solution, but will give us a way to approximate what we need. So which in some cases is good enough for what we need to do. So that's what we're going to try to figure out how to do that. So to do that, this is how it works. So if a differential equation is given in the form of y prime is equal to f of x, y. And let's say it has a solution y equal to y of x near some center point x equal to x of 0. Then this differential equation actually become a way for us to generate higher derivative of y. And if we can do that, we'll then be able to write out a Taylor series for y of x. Then this differential equation can be used to calculate higher derivative of y. As long as y is differentiable. So of course, you might run into a scenario where y is only 14 times differentiable, then you'll be stuck. Okay, but if y can continue to generate derivative, then I can use this differential equation to generate all higher derivatives of y. Using the higher derivative of y, we will be able to generate the Taylor series of y equal to y of x. In some cases, because of what the Taylor series look like, we might actually be able to identify what function y is. In other cases, we might simply just leave the solution to the differential equation in a power series form. Now, so how do we actually do this? Well, show you a very simple example. And the process is actually quite easy to do. It's just a lot of tedious calculation, but it's actually not that hard to actually generate what you need. So show you. So let's say we're given the initial value problem. Y prime equal to y squared and y of 0 equal to 1. We're going to try to solve for by using a power series centered at x equal to 0. Notice that we are given the initial condition as 0. That's why our power series will be centered as 0. So what do I mean by solving using a power series? Well, the power series I refer to is basically Taylor series. So let's go and write out the formula for Taylor series first. So Taylor series for y of x would basically equal to p of x is equal to y of 0 plus y prime of 0 times x plus y double prime as 0 over 2 factorial x squared plus y triple prime as 0 over 3 factorial x to the third plus dot, on and on and on. So obviously we're not going to write out the entire Taylor series. However, if we can actually generate a simple general term or the end term, we will. But if not, we just simply go write out maybe the first 4 terms or something, and just to show what the series look like. Okay, now how do we actually generate this Taylor series? Well, actually pretty simple. All I need is y of 0, which we know. I need y prime is 0, y double prime is 0, y triple prime is 0, and so on and so forth. And the way it works is actually work out very similar to Theorem 13.2.5, where we use to generate higher order of a square matrix. Okay, so show you how that works. So let's start with the following. We do know that y prime is equal to y squared. And we then would know now that y prime at 0 would basically equal to y of 0 squared. And since we know y of 0 is 1, that means it's 1 squared. That means it's 1. So that gives me y prime of 0, because we know y. Now let's try to figure out what to do with y double prime. Well, pretty simple. Y double prime would basically mean the derivative with respect to x of y prime. And so when I differentiate y prime, that means since y prime is y squared, I'm going to say that's the same thing as differentiating y squared. And if that's the case, that would mean that this becomes 2y times the derivative of y, which is y prime. But since I know y prime is y squared, that means this comes out to be 2y to the third. So therefore, y double prime at 0 becomes 2 times y at 0 to the third. That's 2 times 1 to the third, which is 1, which is 2. Pretty simple. Now we're going to do y triple prime. So what is y triple prime? That means you differentiate with respect to x, y double prime. And since we know what y double prime is, that's 2y to the third. I'm going to just say, I'm going to differentiate 2y to the third. And that comes out to be 6y squared y prime, which is 6y to the fourth. So y triple prime at 0 will be 6 times y of 0 to the fourth. That's 6 times 1 to the fourth. That is 6. Now, some of you might recognize that this 2 is basically 2 factorial, and 1 is just 1 factorial, and 6 is technically 3 factorial. Now, we'll do, let's do one more, y to the fourth derivative. So that means I'm differentiating y to the third. So that means I'm differentiating 6y to the fourth. And that come out to be 24y to the third y squared. That's 24y to the fifth. And if I plug in 0, that means I'm taking 24 times y of 0 to the fifth. That's 24 times 1 to the fifth. That is 24. And yes, some of you might recognize that is 4 factorial. So it seemed like this actually follows a very nice and simple pattern here. Seemed to me that I can form a pattern now and say y to the nth derivative would probably just simply equal to n factorial y to the n plus 1. And y to the nth derivative as 0 likely come out to be just n factorial. So this actually come out to be very nice and simple pattern. So now the question is, what do we do with this? Well, what we do is we plug into our Taylor series. So our Taylor series dictate that y of x should equal to, remember, if we're assuming that p of x will convert to y of x, would equal to y of 0 plus y prime of 0 times x plus y double prime at 0 over 2 factorial x squared plus y triple prime over 3 factorial of 0. I'm sorry. Ooh. X to the third, and since we did a fourth one, I'm going to say y to the fourth derivative as 0 over 4 factorial x to the fourth plus dot 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 plus y to the nth derivative of 0 over n factorial x to n plus dot dot dot. And now all I have to do is just plug in all the value that we know. We do know y of 0 is 1, and y prime of 0 is also 1, so it's 1 times x, plus y double prime of 0 is 2 over 2 factorial x squared, plus 6 over 3 factorial x to the third, plus 24 over 4 factorial x to the fourth, plus dot dot dot, plus n factorial over n factorial x to n, plus dot dot dot. So it should be clear that these cancel out completely. And therefore, leave me with this power series for y of x, which is 1 plus x squared plus x to the third plus x to the fourth plus dot 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 plus x to n plus dot dot dot. So that would be a power series solution. And if I want to evaluate y at a specific x value, then all I have to do is just plug that into this formula. Now, of course, here's the problem. The problem is that we are, as I say, we are assuming that y of x and this power series are the same. We have an equal sign. But we actually don't know that is true. We're hoping that this power series will converge to y of x. But we don't know for facts, so let's try to figure out if it does or not. Notice that this series right here is a geometric series. Hopefully you remember what you learned back in Algebra 2. A geometric series has a common ratio of r, in this case r is x, and geometric series only converge if r is between -1 and +1. Therefore, imply that our interval of convergence is actually from -1 to +1. So meaning that this power series will converge to our solution, provided that our x value is between -1 and +1. Anything over that would not work. Now, also, because this is a geometric series, we can actually identify what this sum converges to. So hopefully you remember a infinite sum formula for a geometric series, which is a over 1 minus r. So in this case, I can actually form what we call the closed form of this power series, which is 1 over 1 minus x. So therefore imply that the solution to y prime equal to y squared, y of 0 equal to 1, is the function y equal to 1 over 1 minus x over the interval -1 to 1. That's my solution. Some cases, you will form a power series that you cannot convert into a closed form. Then you just basically write out the power series. So this process illustrates what you have to do to try to solve a differential equation using power series is by first generate higher order derivative and then evaluate them at the center point, which in this case 0. For most of our function will likely be 0. And then form the Taylor series using the higher order derivative you know. And if you form a power series that you can actually generate the interval convergence, then go ahead and try to find that. If it actually can be written in a closed form, then go ahead and do that, and that will be your solution. For most part, if you can actually find the interval convergence, I will ask you for it. If I do not ask you for that, then you can just safely leave that out for now. Hopefully you remember we learned in BC Calculus on how to find interval convergence using the absolute ratio test. But if not, that's okay. Okay, we'll work that hopefully in another videos. Now, how do I know this is the right answer? Well, we can definitely check. So how about we do a quick check? How do I know this is the right answer? Well, let's see. If y is equal to 1 minus x, then y prime would equal to -1 over 1 minus x squared multiplied by -1. Why this is the -1 is the derivative of 1 minus x, so don't forget that. So therefore become 1 over 1 minus x squared. Or maybe I write as 1 minus x to -2. Now if I do double derivative, that becomes -2 1 minus x squared to the -3 multiplied by -1. Oh wait, I don't need second derivative, sorry. So that definitely come out to be y squared, because y is 1 minus x to the -1. And if y is equal to 1 minus x, then y of 0 would be 1 minus 1 minus 0, which is 1 over 1, which is 1. So both of these check out the initial condition and is also satisfied the differential equation. Now, obviously, if you have just a power series, you won't be able to check your answers. But if you do have a closed form, then do try to give it a check just to make sure that you got it right. Now, I'll show you a second example where it doesn't come out to be quite as nice. So this one is a little trickier. Given the initial condition, initial value problem, sorry. Y double prime is equal to y prime, y of 0 equal to 1, and y prime of 0 equal to -1. The problem asks you to solve for y using a power series and show the first 4 non-zero term. Now, this one is a little tricky than the last one. The last one is the first order differential equation. This one is a second order differential equation. It's also not a linear differential equation because you have y times y prime, which is the reason why we won't be able to solve it any other way. The previous example is also non-linear, which is the reason why it's hard to solve this. So how does this one work? So this one we already have two things to start with, where y of 0 and y prime of 0. So it's just a matter of finding y double prime and so on. Now notice that the problem did ask for the first 4 non-zero term. So that means typically it would go up to the third derivative. So we do need to do a little bit of work. So let's see. So we know that y of 0 is 1 already. And y prime of 0 is -1. And we should already know what y double prime of 0 is equal to, because that would just equal to y, which is 1, times y prime, which is -1, so that becomes -1. So we automatically start with 3 numbers, and that would give me the first 3 non-zero term. So to form the first 4 non-zero term, all I need to do one more. So we're going to do y triple prime. So y triple prime would be when you take the derivative of y double prime. And that means you are basically taking the derivative of y prime. So in order to properly differentiate y prime, I will need to use product rule. So product rule dictate that I'm going to do y times y double prime plus y prime times y prime. So therefore become y double prime plus y prime squared. Now I'm going to go and try to figure out what y triple prime of 0 is. So notice all I need to do is plug in y prime and y double prime. So y is 1, y double prime is -1, plus y prime, which is -1, squared. So that come out to be -1 plus 1. That actually come out to be 0. That's no good because that would form a 0 term. So we have to go on to next term, and hopefully the next term is not 0. So let's see what happens. So y to 4th derivative. That will be the derivative of y triple prime. So that means I'm taking the derivative of y double prime plus y prime square. So once again, y oh, okay, you know what? Maybe I'll do the following. You probably okay. It's okay. I'm just going to leave it. Okay, so let's go ahead and take the derivative of this thing. So that would be, once again, product will become 1 y times y triple prime plus y prime times y double prime plus y prime square would be 2y prime times the derivative of y prime, which is y double prime. So notice that just required me to know y triple prime, y double prime, y single prime, and y, which I know all those values, so I'm going to evaluate. So y to the 4th derivative of 0 would equal to y, which is 1, y triple prime we get 0, plus y prime, which is -1, y double prime, which is also -1, plus 2 times y prime, which is -1, and y double prime, which is also -1. So it seems to me that this come out to be 1 plus 2, which is 3, which is good. It's non-zero. So now I'm ready to write out my power series for y. So y would equal to y of 0, which is 1, plus y prime of 0 times x, so become -1 times x, plus y double prime of 0 divided by 2 factorial x squared, plus normal is a third, but then that one is 0, so now I need the 4th term. So that will be y to the 4th derivative of 0, which is 3 over 4 factorial x to the 4th plus ... Now, I don't see any pattern here, so you're probably not going to be able to write out some kind of general term. But I can clean this up, so I'm going to clean this up. That means y is equal to 1 minus x minus 1/2 x squared plus 3 over 4 factorial is actually 1 over 8 x to the 4th plus ... So when you're doing this process, important to remember that every time you differentiate y, you have to have a derivative of y. If you differentiate y prime, you have to have a derivative of y prime, so on and so forth, because you are differentiating them with respect to x. So therefore, chain rule need to be applied. So in here is very similar to implicit differentiation that you learn in BC calculus, where you differentiate function y, you have to put dy dx. We just put y prime instead, and if we take differentiate function of y prime, then we need the derivative of y prime, which is y double prime, so on and so forth. It's not hard to do. It might seem a little weird at first when you do this process, but it's actually come out to be pretty simple once you get through a whole bunch of them. All right. So I think I will stop today's video here since it's about 25 minutes already, and we'll continue on more example on our next video. All right, talk to you guys then. Bye bye.